In this video, in this precalculus algebra video, we're going to define parabolas geometrically. Now, we've already talked about parabolas like in your intermediate algebra class and earlier in this class as well, but that was from a purely algebraic perspective. Now we're going to talk about parabolas geometrically. We're going to define them geometrically so that we can get at important features that are hard to talk about simply algebraically. Like, for example, I just graphed this little parabola over here, and it turns out that if sunlight, for example, comes in, so this parabola has an axis of symmetry, and if sunlight comes into this parabola like so-and-so, it reflects off, let's say this was like a mirror dish or something like that, it's a reflective dish. It's going to reflect into a point right here called the focus. Okay, so sunlight comes in and it reflects and it focuses there. Now, it doesn't matter where the ray of sunlight, so it can come in like this as long as it's parallel to the axis of symmetry, and it's going to reflect back to the focus. And so if you have a lot of rays of sun coming in like that and they're all reflecting back to this point right here, well, what's going to happen to anything at that point? Well, it's going to heat up, right? So currently and historically as well, people have used parabolic surfaces for the reflective property so that you could focus things right here, whether it be sunlight or other type of electromagnetic waves. In fact, they use satellite dishes are shaped parabolically, as you've noticed, right? You drive by and you see a satellite dish. Why is it shaped like a parabola? Because it has this reflective property. Electromagnetic waves coming in will focus here. So if you put a pickup right here, then you'll be able to sense all the waves will converge here, and you'll have a strong signal for whatever you're trying to detect. So this point isn't on the parabola. So the way we make use of, the way we talk about parabolas in a geometric way to make use of this point is we define parabolas geometrically to access things like this that aren't obvious from an algebraic perspective. So what we're going to do to define parabolas geometrically is we're going to start with a point on the y-axis right now, and we're going to call it the focus. So this point, it's not going to be on the parabola, but it has geometric significance when you apply parabolas in different situations. So that point, let's give it coordinates 0p. So this will be 0p on the y-axis, okay? So p is the y-coordinate of that point. Now when you do that, we're also going to define a line. So now that you have these coordinates 0p, you're going to create the line below the x-axis, y equals negative p. So we're going to have a line through this point, and it's going to be y equals negative p. So in other words, this point right here, which is going to be on the parabola, it's the same distance from that point called the focus and this and the line that we're going to create, or this point for the moment. So what we're going to do is we're going to create the set of points, or we're going to draw the set of points that are equidistant from the focus and the line that, let's draw this line in, right? This line's called the directrix. Let's get that line in right now. So this line that I just drew, through that has the equation y equals negative p, it's called the directrix. And what we're going to do is we're going to create a set of points in the plane where every point is as far away from the focus as it is from the line, from the directrix. Like, for example, this point is obviously equidistant from the focus and the directrix. What about this point right here? So that point right there, how far is it from the focus? Well, that's the distance right there. But you can see that distance is about the same as that distance. So this point is going to be on the parabola as well. So we're going to define the parabola to be the set of points where every point is as far from the focus as it is from the directrix. What would another point on the parabola be? Well, it'd be like maybe right here. Why? Because that point is as far from the focus as it is from the directrix. Another point might be like right here. So I'm drawing these points. I'm just kind of eyeballing that distance, and I want it to be the same as that distance. And if I keep doing that, right, all these points, right, they're all as far from that focus as they are from that line, okay? And then now, of course, you can do it that direction, but you can also do it this direction as well. Right? These are all the points that are, again, as far from the focus as they are from the line, the directrix. So in that way, we're creating a, you can see these points are forming a parabola, but we're creating the parabola using a geometric definition, right? The points that satisfy a certain criteria, and that criteria is that they're as far from the focus as they are from the directrix, okay? And if we keep doing that, we're going to get a solid curve, and that curve is going to be our parabola. So let's go ahead and graph that curve in now. Okay, so I went ahead and graphed our parabola in there, and I also wrote this definition, the parabola. This is a geometric definition that we're going to use. It's the set of points in a plane equidistant, so equally distant from two things, from the focus and the directrix. So here's the focus, right? This focus had coordinates 0p. Those got erased. So 0p, and then the directrix is the line y equals negative p, where these are the same p, right? This is the negative of that. So let's go ahead and write down. So if you have that condition, right? If you say that, oh, any point on the parabola xy that satisfies those criteria, if you go ahead and use the distance formula and then set those two distances equal to each other, you can convert that geometric definition that you started with. That'll give rise to an algebraic equation. And the algebraic equation for the parabola happens to be this: x squared equals 4 times p times y. Now, this kind of looks like a parabola you've seen before, but what's new is the p. You might say, what's the meaning of the p? The p is the y coordinate of the focus. Okay, so we started with that p, and that p shows up here in the algebraic formulation where we started with that definition. So the vertex is at the origin. So in this case, we're simply working with parabolas that are unshifted, that have their vertex at the origin. In a few sections, we're going to go ahead and talk about how to shift parabolas based upon this definition. And it turns out we're just going to use transformations. But right now, the vertex for these problems is always going to be 0, 0. And you can see that, right? When x is 0, y is 0. That's obvious. And the focus is what we said it was going to be. It's the point 0p. So the focus is the point 0p. And the directrix is this line, y equals negative p. Directrix. It's a strange word. Y equals negative p. And let's note that here, p is greater than 0, right? So I drew p on the positive part of the y-axis. So here, p is greater than 0. And if that happens, so if you are working through these problems, and you start with an equation like this, and you find that your p is greater than 0, then your parabola opens up, like it does in this graph up here. Now, sometimes we're going to have examples where p is less than 0. And what do you think is going to happen in those cases? Exactly, right? In those cases, if p is less than 0, the parabola is going to open. In that case, it opens down. So if you have a parabola of this form, it either opens up or it opens down, and it all depends if p is positive or negative. Now, one more thing to keep in note, that when you graph these, like we're going to do in a moment, it turns out one of the first things you want to do is identify your focus and your directrix. And once you find your focus, the parabola always sort of opens around the focus. You see how it kind of opens towards the focus? That's something to keep in mind when we are graphing these problems. Let's do an example now, see how this works. Okay, so let's find the focus, the directrix, and the focal diameter, and we'll see what that is in a moment, of the parabola x squared plus 2y equals 0, and then sketch the graph of the parabola. Okay, so the first thing you want to do is put this in standard form. Now, standard form, let's go back to the previous page. Standard form is when you have the quantity that's squared by itself. That's not like standard form before, right? So, oh, sorry, I got a little messy. So just remember, when you're doing these, what we do is we isolate the quantity that's squared. And that quantity, as we're going to see in another example, that quantity is sometimes y squared. So it's not always the case that x is squared, even though it is in this problem. Okay, let's go back to our problem now. Okay, so we're going to isolate that x squared. So we're looking at, we start with x squared plus 2y equals 0. And isolating the x squared, we have x squared is equal to negative 2y. Once you've done that, you want to compare it with the standard form. And the standard form, as we saw on the previous page, is x squared equals 4py. So what you want to do is you want to identify what your p is, right? So I see x squared and y, and what is p? Well, the 4p I can see has got to be negative 2. So I write that down. That 4p is negative 2, so p is equal to negative 1/2, okay? Now, remember the focus has coordinates 0p on the y-axis, but p is negative. So we're down here, right? This is negative 1/2. And that means, remember the parabola has a vertex at the origin, and it opens towards the focus. So the parabola is going to open like this. So let's write down that the focus, which always has coordinate 0p, in this case it's going to be 0, negative 1/2. And the directrix, right? That always is the equation y equals negative p. But here, p is negative. So if p is negative, that means it's the negative of negative 1/2. So it's negative 1/2. So the directrix is y equals 1/2. So the line y equals 1/2, which is up here, let's draw that in now. Right, if this is negative 1/2, then this would be positive 1/2. Let's draw that line in. Okay, and that's our directrix. So our parabola is going to open, or it's going to open downward, and it's going to look like that. Now they ask us for one other thing in this problem. They ask us for the focal diameter. Now it turns out the focal diameter is always this. And we'll see what this means in a moment. The focal diameter is always the absolute value of 4 times p. So in this case, it's the absolute value of 4 times, let's see, p is negative 1/2. So it's the absolute value of negative 2, which is positive 2. Okay, that's in this case the focal diameter. So if we graph in this parabola, keeping in mind that we always want it equidistant, the points are equidistant from the focus and the directrix, right? So the parabola is going to look like this, because all the points have to be the same distance from that point as they are from that line. So let's graph that in now. Okay, so there's the graph of our parabola, and you can see that every point, so here's a point on the parabola, for example. If you were to walk to the focus, that's about the same, that is the same distance as if you walk to the directrix. Now, what's the meaning of the focal diameter? The focal diameter is the width of the parabola if you measured it through a line through the focus parallel to the directrix. So for example, if I'm right here, right, so I'm going through the focus, but I want to go parallel to that line there. So that would be this length right there. And why is that length equal to 2? Well, what's the length from here to the x-axis? That length is the same as this, right? So this would be 1/2. Now, that is also the same distance. If this is negative 1/2, remember this has the equation y equals positive 1/2, right? So if that distance is 1/2, that distance is 1/2 as well. So if you were to walk from here to here, that would be 1/2. And then another 1/2. So this would be the distance of 1. Okay? Now because this point's on a parabola, the distance to the directrix, which is 1, is the same as the distance to the focus. So if that's 1 as well. So if that's 1, then double that all the way across, that's 2. So that length right there, called the focal diameter, is the width of the parabola as measured through the focus. That length for this parabola is equal to 2. And that's important, right? Because we want to know how wide is a parabola in applications. Now it turns out that parabolas opening up or parabolas opening down aren't the only game in town. They can also open to the right, or they can also open to the left. Now if they open left and right, they don't look like this. The x and the y are basically switched. Let's see an example of that now. So here's a parabola that opens to the right, and once again it's opening around the focus. But see how the focus has coordinates p0? That's because the focus is on the x-axis. The p coordinate is the x coordinate, or x rather, the p is the x coordinate, I should say. And now notice at this line, the directrix is no longer horizontal, now it's vertical, and its equation is x equals negative p. And this would be the equation of that parabola. y squared equals 4px. It's not a function because it doesn't pass the vertical line test, right? But it's still a curve that's of interest in applications. Now, let's write down what we know. We know that the vertex, once again, the vertex is still 0, 0. The parabola still goes through that point right there. The focus now, instead of 0p, the focus is p0. And then the directrix, right, is the line x equals negative p. It's a vertical line. Now in this case, p is greater than 0. And if p is greater than 0, that means it opens to the right, like this. So if p is positive, it opens right. And if p is negative, then it opens left. So sometimes we're going to have parabolas that open like that, in which case the focus would be here and the directrix would be over there. Okay, let's see an example of how to handle these, like we did the previous ones. So let's find the focus, the directrix, and the focal diameter, once again, of the parabola x equals 1/3 y squared equals 0. So the first thing to do is isolate what's being squared. So we take x minus 1/3, y squared equals 0, and we isolate that 1/3 y squared. And so x equals 1/3 y squared. Multiply both sides by 3. 3x equals y squared. So let's write that as y squared equals 3x. And now you want to compare that with the standard form for a parabola that has y squared. And that standard form is y squared equals 4px, like we saw on the previous page. So if we set 4p equal to the 3 right here, right, we find that we get 4p is equal to 3. So p is equal to 3/4. That means the focal point, or rather the focus, has coordinates 3/4, 0. The directrix is the vertical line x equals negative 3/4. Okay, let's draw on what we've got so far. So here's 3/4, right? And then negative 3/4. The directrix would be there, and it's a vertical line, so we can draw that in. So, okay, and our parabola goes through this is the vertex, goes through the origin, and it's going to open to the right. Let's go ahead and draw that in now. So there would be the graph of our parabola, right? And then finally, let's find our focal diameter. So our focal diameter is always equal to the absolute value of 4p, which in this case is the absolute value of 4 times positive 3/4. So we're looking at 3. And so 3 is the width of the parabola. So width of the parabola as measured through the focus, with a line parallel to the directrix. Okay, so in the next video, we're going to talk more about starting with the equations of parabolas, and building the equations of parabolas given information about focus, directrix, and focal diameter. Okay, until next time.